Forces Lesson 2. So you're back. You watched the first one and you liked it and you came back. Or you haven't seen the first one and you're seeing me for the very first time. Either way, yay! If you didn't see last week, all you need to know really is that we looked at one of Newton's laws. And one of Newton's laws says that if you get something that is still, we looked at how you could apply a force. A force is just a push or a pull. How could you push or pull this still thing so that it doesn't move? Okay, if it's not moving, how do you push or pull it to make it still not move? Well, there's two things you could do. You could push on it with the same amount of push in both directions, like that, so it's not moving, or you could pull it in both directions, couldn't you? As long as it was a good sturdy, robust little Lego horse, then it still wouldn't move. That's because the forces that you're putting on it are balanced. You're pushing the same amount on both sides, or pulling the same amount on both sides, so the forces on it are balanced. And if the forces on a still thing are balanced, then it will stay still. How would you make it move? You would apply an unbalanced force. So if you're pushing a little bit more with this hand, then the forces wouldn't be balanced and the horse would move. That is really, sorry to waste your time, people who came to last lesson, it's really all you need to know to watch this lesson. Okay, so that was one of Newton's laws, right? That was Newton's first law. Now, observant people will have noticed that if that's Newton's first law, there are probably other laws. There are. Today we are learning about Newton's third law. I'll tell you it very quickly and then we'll just do an activity and you'll get it, I think. So Newton's third law is that for every action there is an equal and opposite reaction. Now, what this actually means is if you're standing up or you're sitting on a chair, then your weight, we'll do weight next lesson, but your weight is pulling you down onto the floor. So you are pushing down on the floor, right? With a force. The floor is pushing back on you. It sounds weird, but that's all Newton's third law really means, is that when you push on something, it pushes back on you with a force that is equal, but acting in the opposite direction. So you're pushing down on the floor or on your chair, and the floor on your chair is pushing back on you. So we looked last week very quickly at how force is measured in newtons. If you're pushing down on the floor with a force of 50 newtons, the floor's pushing back with a force of 50 newtons, but it's pushing in the opposite direction, so the forces are balanced out, okay? If the forces weren't balanced, if the floor pushed back with 100 newtons, then you would go flying into the air, just like that horse moved when the force on it was not balanced. So that is Newton's third law, but let's have a look at it in action, all right? So get a plastic bottle for me and dunk it into a washing up bowl full of water if you've got those things. If you haven't got those things, then just get a plastic bottle at any point, get into the recycling before you have a bath and do this in a bath, it's good. But just all you do is squeeze this bottle, okay? And feel what happens. So you've filled up a bottle with water, you've put it in a bucket of something of water, and just feel what happens. The only motion that I'm doing is this. I'm not pushing it forward. Yeah, Newton's third law is why you can swim. Yeah, it's why everything really. So have a push. What do you see and what do you feel, more importantly? You should feel a force, and you can actually see from this which direction the force is going in. Can you see? The bottle's moving backwards, isn't it? It's moving that way. Now, why is that happening? Well, what's happening is Newton's third law in action. So water, when you squeeze, you're pushing water out of the bottle from this direction here. Water is being pushed out of the bottle in this direction. So Newton's third law says that if the bottle is pushing on the water is also going to push on the bottle with a force that is equal and opposite. So you'd notice that the harder you push, the more force your bottle feels, the further it goes backwards, because the harder the water pushes out this way, the harder the bottle goes back. So that is genuinely how octopuses and squid swim. They've got a sort of like this kind of an empty balloon in their body called a mantle, and they fill it up with water, and then when they want to move, they squeeze the water out through something called a siphon, kind of just like this, just a tube, and that's how they go. Jet-propelled squids and octopuses, and it's the same with rockets. So obviously, rockets is not water; they've got chemicals inside, and a chemical reaction happens when those chemicals get very hot, and gases are produced, and the gases fly out the bottom of the rocket with terrific force and because the gases are being pushed out of the rocket, Newton's third law says that the rocket gets pushed in the opposite direction. Sadaf coming in with a comment at exactly the right time. Yes, it is the same with a space rocket. So yeah, you've got to be a little bit careful. There's a misconception, that means a lot of people think it, but it's not true, that a rocket goes up because the ground pushes down on the rocket. But forces come in pairs, and you've got to be careful what the pairs are. So if the rocket's pushing down on the ground and the ground's pushing down up on the rocket isn't going anywhere. That would be the pair, just like you standing on the ground. But if you release a lot of hot air from a rocket in this direction, then it's the rocket pushing out the air which causes this force to go in the opposite direction. Okay, so just watch out for your pairs. Okay, I think you know enough to do an octopus themed question. Here we go. I'm gonna flip you again. Bit of literacy for you today. I was saying yesterday, it's a bit weird, isn't it, how we put all subjects into little categories at schools, because obviously not really like that. Scientists do need to be able to express themselves well using words. Here we go. So a little question for you. Please explain, by talking about the forces acting on an octopus, how it moves forwards. So some people last week complaining that I went far too fast, and some people like, oh, you could have gone much faster, I knew it all already. So a bit for everybody then. This is what I would really like you to do. Use these words to complete this sentence. An octopus fills its body with water, and then what happens? But if that's too easy, or you've got a bit of science behind you already, if you're older, you could use these words as well. Equal, opposite, force forwards, and Newton's third law. And when you've done that, if you're a thinker, you're finding this easy, or you're a bit older, have a go at this brain exercise. I'll be very, very surprised if you get that. That's kind of GCSE level thinking. And now I will try and stay silent, but if anyone's got any questions, now is a good time. The octopus then pushes out the water, which thrusts it forward. No, age 10, what a great word. Yeah. Thrust, very good word for something that propels something forward. Let's do some arrows, would that help? So yes, you could well say that this force, thrust, you could well say that force was a thrusting force. Ah, Michelle, there is no gravity. Well, there is always gravity, but there's also always a reaction force pushing back up. So if later on we'll do a question about hot air balloons, and then gravity is relevant because a force is pushing against gravity. And quite often, yeah, at GCSE you'll get a question that says draw all the forces acting on the thing, and gravity is like always a good 1 mark. Ah, David says the force must be unbalanced. In the brain exercise, the force must be unbalanced for something to move. So, because we did this last week, if you push a ball in one direction, then the ball moves. But if you're pushing the ball with a force of like 2 newtons, and Newton's third law says the ball's pushing back with a force of 2 newtons, then why does it move, David? Right, I'll answer in 2 minutes. The ball moves because you're pushing it. Yeah, well, that's true. But how does it move? Anyway, this is something that I'll answer right at the end. All right, let's go then. So, an octopus fills its body with water, and then a lovely, simple and totally correct answer that quite a few people have given me now. An octopus fills its body with water, then pushes the water out, which means the octopus moves forwards. You could just say that. The octopus pushes the water out of its body. So to add a few of these words, the octopus pushes the water out of its body, so the water pushes back with a force that is equal and opposite, and the octopus moves forward. And that is Newton's third law. Or the octopus fills its body with water, pushes the water out, and then Newton's third law says that the water will push back on the octopus with a force that is equal and opposite. Is that okay? This one, I'll go through this one now. Yeah, it's to do with what the force is acting on. So you've got a ball here. You push on the ball, like that. the ball pushes back on you. It's a very common misconception. It gets people a lot of confused about Newton's third law, because if you push on the ball, then the ball pushes back with a force that is equal and opposite. But we've just learned that if the force is on something of balance, then a still thing doesn't move. So how does it move? You only think about the forces acting on the object. So if we only think about the forces acting on the ball, then yes, the ball is pushing back on you, but that doesn't really matter. We're not interested in that force. Like, the ball will push your finger a teeny tiny bit in that direction, but we don't care about that. If we're thinking about the movement of the ball, the only force acting on the ball is your push. The pair of that force is just pushing back on you, so it doesn't really matter. Okay. Right, so I did call this lesson Resultant Forces. Shall we have a talk about resultant forces? A resultant force is like the overall force acting on an object. I'm not going to tell you what resultant force is, I'm just going to hold this up and flip the screen, and you can have a look and see if you can. I think it'd be easier to just use an example for you to try and kind of work out resultant forces. So imagine that you and your friend find an enormous biscuit and you start fighting over it. You pull the biscuit this way with a force of 6 newtons, and your friend pulls the biscuit in that direction with a force of 4 newtons. It's a well-made, robust biscuit. It doesn't break. Who gets the biscuit? And then the second part of the question is, what overall force is acting on the biscuit? What force does the biscuit actually feel? So if you were both pulling with 4 newtons, it's like the example with the little Lego horse at the beginning. If the biscuit was still and you both pulled with 4 newtons, the biscuit wouldn't move. But you've got an extra 2 newtons here pulling on your side. So who would get the biscuit? Yeah, hopefully it's fairly obvious, isn't it? You would get the biscuit because you're pulling with more force. What overall force is acting on the biscuit? You might think it's 10 because you add the forces together, but actually, because the forces are acting in opposite directions, the overall force is 2 newtons. The resultant force, well done, David. Although if you didn't get that right, then of course you wouldn't. I haven't told you what it is yet. You're exercising your brain. We say that the resultant force, the overall force acting on the biscuit, is 2 newtons because the 4 newtons on this side and the 4 newtons on that side cancel each other out, and you're just left with 2. So the force that the biscuit feels is 2 newtons in that direction. Okay, this is the point where I would look you all in the eye and say, is that okay? And look at the people who are about to cry and come to you next. But I can't do that. So I'm going to give you a question sheet in a minute, and then you can tell me in the comments if you're not sure. First of all, for a quick recap, force is... Oh, I'm a proper teacher now. My whiteboard pens have started to run out. Guys, I'm so proud. We've been doing this for long enough. Force is measured in newtons, length is measured in meters, time is measured in seconds. Force is measured in newtons, or you could use a capital N, not small n, capital N. What actually is a newton? 1 newton is enough to accelerate, move 1 kilogram. It's enough to move 1 kilogram 1 meter in 1 second. So for example, yeah, giving away too much of my lifestyle really, but if you take this 1 kilogram bag of couscous, if I could move it up 1 meter in 1 second, then I would have pushed it with a force of 1 newton. Just to give you an idea what newtons actually are. Right, yeah, I'll give you a question sheet. I'll go through the example with you, and I think you'll probably get it, you know. I would like you to please look at these examples below and tell me the number of newtons that the resultant force is, and also what direction is the force acting in. Force always acts in a certain direction, so you've got to give the direction as well. So here's my example. I've got a ball that is starting to fall off a cliff. It's just starting to fall, so gravity is pulling it down with a force of 10 newtons, and air particles are pushing up on it, but only with a force of 5 newtons. So the overall force, 5 newtons upwards from the air resistance and 5 newtons downwards from gravity, cancels out, and overall the ball is falling with a force of 5 newtons pulling it in that direction. All right, have a go at this. Oh, Fiona and Antonia, Bam, straight in there with answers. Antonia saying 15 newtons, careful. There's 50 newtons on this side, a force pushing it forwards with 50 newtons, but there's also 10 newtons dragging it backwards. So overall, the 10 newtons pulling it backwards, like friction, and the 10 newtons pushing it backwards, which is friction, and 10 newtons pulling it forwards, they cancel out. So the resultant force is like what force is left when you've cancelled everything out. All right, let's go through some of these. I'll just do the first two so that you get the idea. So the resultant force for this one, 10 newtons is pushing back because of friction, but there's 50 newtons pushing in this direction. So 10 newtons and 10 newtons cancel out, and you're left with the resultant force is 5 newtons, and the force is acting in that direction. Number 2, we've got a rolling hedgehog. So we don't know which way it's rolling, but it's got 8 newtons acting in that direction and 2 in that direction. So 2 and 2 on that side would cancel out, and you're left with 6 newtons going in that direction. And shall I do the hot air balloon as well? Oh good, yes, lots of people saying 5. Just reading some comments. 2, 6 newtons on the left, yes, exactly. Vicky, you're 11, that's good, isn't it? Andrea's 9, marvellous. Hot air balloon, you've got, we'll assume it's going up, we've got 50 newtons of hot air pressure pushing it upwards from inside, and 20 newtons pulling it down because of gravity. So overall, the resultant force is 30 newtons going up. The sledge one. It's a bit sneaky, wasn't it? Did you get that on the sledge? Am I going at an okay speed? The resultant force, overall force on the sledge is... well done, Sarah. Yeah, 0. So it doesn't have a direction. People who came last week, think about how that sledge could be moving. Cat sliding on the ice. Did you get that one? The resultant force on it is just 20 newtons. It's going that way. And if you did these ones, then this was just to get you thinking. If the forces are acting in the same direction and they're on the same side in the same place, hello Charlotte, then you add them together. So overall, the force acting over here is 8 newtons. So that would cancel out with the 2, and it would be 7 newtons acting in that direction. Some clever clogs yesterday was like, oh, but you know, what if one was like there and one was there? Would it spin? Yes, it would. We're going to do turning forces in, I think, lesson 4, a couple of weeks' time. And this one, I'm going to come back to that one actually. We will end the lesson there for Key Stage 2ers, people who are sort of under 11 who feel like they have done enough, because that was a lot. Let me flip my screen again. Exactly, sledge could be still. It could be still. David, I'll explain in a minute the other things that could be happening to that sledge. Right, but yes, we're going to do a natural pause in the lesson now. So some of you will have noticed that we've done Newton's first law and we've done his third law. Some of you will just be burning to know what Newton's second law is and to do some GCSE questions. I will do those in a minute for you. But if you're a bit younger or you haven't done much science before, now would be a good place for you to just pat yourself massively on the back. Congratulations for making it this far. This is all physics that will come up again at GCSE and that you wouldn't really learn until you were 11. So if you've understood some of that and it's enriched your understanding of the world, then very well done. I'm going to put my little advert in here because I know that some of you have to go at a certain time anyway, and then I'll do a few extra bits for the people who want to stay. So hello, my name is Lara. I'm running this science communication company called Theatre Science. Started doing these science shows every week in the first week of like lockdown in March, and then I just kept going. And I am still going because some lovely people have gone to this website that I've set up called Patreon, where you can support me with £3 or £5 or £10 a month, and you get various thank yous for supporting me. So if you go to my Facebook page and you click sign up, kids, I'm not talking to you, don't you do it, this is just for grown-ups. If you click sign up, it takes you to my Facebook page and explains, like, if you sign up with £3 a month, I send you these cool rainbow glasses that make you see rainbows, and if you sign up with £5 a month, you get my magazine delivered once every 2 months, and the one that I've just finished and I've given to my husband to look beautiful because he's a graphic designer is on snow, and it's all about like the science of do Yetis exist, and there's a little snowflake spotting guide, like different ones that you can see and how snowflakes form, and I'm very proud of it. Yeah, that's it really. I'm just very excited by it. So I don't know, some people have like a home ed budget, or if you feel like supporting, that would be wonderful. If you're not in a position to support, that's kind of the point, because physics free for everyone, amazing. The business model seems to be working, it is growing. But if you're not in a position to support, or you just don't want to, you like my Facebook page, that would be very cool. Or you could go to my YouTube channel and click subscribe. That would also be very cool indeed. That's it. Right, those of you that are left, I'm going to assume Megan and Sophie in Italy, you are most welcome. Thanks, Sadaf. Magazine is awesome. Take it from Sadaf, not from me. Right, I'm going to assume that the people who are left are in this, and you want to know a bit more detail. Okay, so let's talk about Newton's second law, because that does not come up for quite a long time at your age. Newton's second law is something that you might have heard of. F equals ma. Force is the F, and the m is mass, and what's the a? And we're gonna, I can put it on. Acceleration, which just means how quickly something is speeding up or slowing down. Made it. Yeah. Force equals mass times acceleration. All that really means is that the force that you're applying, how the thing behaves, it also has to do with its mass and its acceleration. So for example, if you had a massive rocket and you combusted just a few chemicals and like 3 gas particles came out of the rocket, then yes, the rocket would be pushing the gas particles out and the gas particles would be pushing back, but the rocket would not move. And that's because the rocket wouldn't accelerate, because the rocket's mass is very, very big. So you'd need a much bigger force to accelerate a rocket. If it was like a flea that did a fart, I don't know why my brain always goes here, but if it was a flea with a teeny tiny mass that ejected like 3 gas particles from itself, then it probably would accelerate, because it wouldn't need a very big, because this number is small, so this number would be big, see, if this number's the same. That's why when people go up in rockets, they have to eat like weird freeze-dried ice cream and stuff. They can't take like their favourite bars of dairy milk with them, because mass is incredibly important when it comes to flying rockets. The more mass you had, the more force you'd need. So astronaut isn't allowed his dairy milk, because that would just be more expensive and more complicated, because you'd need even bigger explosion than you already have. Right, what else was I going to tell you? Oh, let's do this. If you came last week, let's have a look at this question here. This describe how the objects in questions 1 to 5 could be moving. There's more than one choice for each. If you came last week, then the easiest one to start with is the sledge. So last week we looked at how if the forces on something are balanced, if it was still already and the forces on it are balanced, then it stays still. So it's possible that 2 people are both pulling the sledge in opposite directions, fighting over it, and the sledge is staying still. But we also looked at how if the forces on something are balanced and it's moving at a constant speed, then it just stays moving at a constant speed if the forces on it are balanced. So it's possible that this sledge is moving at a constant speed, and this one, I'll only do one more because it's super weird. This one, we're assuming, aren't we, that the trolley's moving forwards. You're pushing it with 15 Newton worth of force. The supermarket floor is pushing back, the friction is pushing back with 10 newtons, and so you are speeding up. It's not moving at a constant speed. You're legging it through the supermarket, getting faster and faster and faster because you're late or something. But what could be happening is that you could have quickly pushed the supermarket trolley, you could be pushing it backwards. You could be pushing the trolley backwards with a force of 10 newtons, and friction could be pushing back with a force of 15 newtons, in which case the trolley is travelling in this direction and it's slowing down. So that's just a thing for people who are like, yeah, I know all this. No, you don't. I don't either. It just, the more you want to learn about physics, the more it gives you. It just gets weirder and weirder and more complicated. Right, on that note, let's do GCSE questions and then we will finish. I will leave you alone. GCSE question number 1. You can put this in your own words. The diagram shows an aircraft and the horizontal forces acting on it as it moves along a runway. We've seen this image before. I couldn't give you this question last week because you didn't know about resultant force. So it's moving along a runway. The resultant force on the aircraft is 0. What is meant by the term resultant force? Hi from England. Mel, you can play the electric bass. I can play the electric bass too. Focus on the question. Oh, people are just showing off now. Right. What is meant by the term resultant force? Hello, Northern Ireland. This is that super awkward bit of a lesson in a class of kids where you're like, right, that ends our lesson on resultant force. What is a resultant force? And they all go, well, I don't know. Hiya, Deacon. In Birmingham, one of my favourite places. Yeah, you can. Right, the answer is, I would not expect you to get the first one, a single force that has the same effect as all the forces combined. But look what they'll accept. All the forces added up, or the sum of the forces, don't worry about that, that's because we haven't looked at minus signs. Overall force, yeah, exactly, well done, Sadaf. If he said the overall force, well, you're all right, I like it, it's funny. If you say overall force, then you got a mark. And the next question, which is super hard, it's killed people at GCSE. The diagram shows a boat pulling a water skier. The arrow, this little white arrow here, represents the force on the water produced by the engine propeller. All right, so this is a boat. My screen flips, so it's weird. This is a boat. The boat's got a propeller, and the propeller is pushing on the water in this direction. So the arrow shows you what direction the propeller is pushing on the water. This force causes the boat to move. Explain why. Like, so many people going, what? I'm not explaining that. The clock is ticking. Just skip it, move on. Alice, you're very welcome. Should I tell you? For 2 marks as well. What are your marks, do you reckon? I don't know if I would have got this right. A lot of people in tears when we went through this after the exam. Not in tears, just cross. So the propeller pushes on the water. The force causes the boat to move. Explain why. The propeller produces a force from the water on the boat. So if you said that the water pushes on the boat, you'd have probably got a mark for that. And if you said in the forwards direction or in the opposite direction, then that was your second mark. So well done. I just think it's interesting looking at mark schemes. Like I say, you just got to be so specific. So what you've learned, you learn and you know it, but you've also got to be able to translate it correctly into an exam question, haven't you, if you want to do GCSEs. So if you just said produces an equal opposite force, you would have got 1 mark. Oh, hello. Kim, the force is pushing the water and the opposite force is pushing the boat. Yeah, you'd think so, wouldn't you? I think you'd have got a mark for saying the opposite force is pushing the boat. You would probably have had to say where the force comes from. Right, that is the end of this lesson. And I've even already given you my outfit. So I can just check through that I haven't missed anything, and I haven't, and just say thank you so much for coming. It is so lovely reading all your comments. It really feels like you're with me. Scarlett and Elliot, you are most welcome. Right, I'm going to say bye, thank you so much for coming, and I'll see you next week. So I can edit it there for my YouTube channel, but I'm also just going to say bye. Yay, I am 9, says Michelle. What have you talked about the third law, says Sada? Yeah, well, that is the third law. Yeah, it's true.